So this is VideoJAM. I didn't know exactly if I wanted to make a video on it or not. It's a very short paper. It's not very long. It's not very complicated, but I think the idea is very cool, and I kind of wanted to talk about it a little bit. Some ideas with it because it's a very simple idea. I mean, this video probably isn't going to be that long, but I just wanted to talk about it. Like the current state of video models is kind of underwhelming, but I feel like this is a very good direction for video models to take. I don't know if a paper like this has been created before. Basically, they add motion to it. I'm guessing it has, but this is the first one I've seen, and it's a simple idea, and I just wanted to talk about it. So, I'll just talk about kind of the current state of like video models, and then go from there. Like essentially, if you want to model an image, you do that via diffusion. So to do that, you basically have your image. Draw an image of a good old cat here, and basically you slowly add noise to it over time steps until you get a pure full noise image, where this is, say, x0 and this is x1. And you do this through an iterative process where you can do whatever process you want. Like there's a bunch of different types of diffusion processes, but the current go-to one is flow because it's easy and it works quite well. So x at time t is going to be equal to t times x0 plus 1 minus t times your noise. We'll just call it epsilon, where epsilon is sampled from a standard normal distribution. So I don't know why I drew this blue, but whatever. So you have a diffusion model basically reverse this process. So takes the noise, converts it to an image. That's done with the transformer, obviously, because everything uses a transformer. Now, how do you model video? Well, to model video, all you do is you do the exact same process, except you add multiple frames and you add noise in the exact same way. So if I have multiple frames here, maybe x at time, some intermediate time step is some intermediate noisy representation, but you add noise in the exact same way. So x at time 1 is going to be our full noisy Gaussian images here, x at time 1. So x at time t is going to be equal to the exact same thing here. All you do is you change the dimensions of x0 and epsilon. So here x0 is of shape 3 by, or height by width by 3. I'm not adding an alpha channel. Here, x at time t is going to be of shape t by h by w by 3. So all you do is you add the time, all you do is add time. So you just stack this, and that's all you do. So how do you model this? You model it with the transformer. So basically your image, you have your image here, say image of a cat. That is terrible cat, whatever, good enough. Looks like a demon. So yeah, you take your image of a cat, you then split it up into a bunch of patches. So this is just normal DIT, where this patch here goes here, this patch here goes here, and you flatten these patches. So maybe this is of size 16 by 16, so you would have a 16 by 16 patch, you flatten it to 16 times 16, that'll be your new dimension, and now you have a sequence of tokens that you can then throw through a transformer. It will then give you a prediction for each of these tokens, and then you recombine these to get your output prediction, where your output prediction is going to be the velocity of the velocity prediction, basically pointing in the direction of the added noise. So normal image modeling. What you initially did whenever video models were first kind of introduced is you would add a temporal attention mechanism, but instead what you can do is, like, you can add a temporal attention. You can add attention over time and attention over pixels, so you can have both types of attention. Alternatively, you can just take your images, segment each of these, and then convert this to just a larger set of tokens, where the first, say, 9 tokens here would represent the first image, the second set would represent the second image, and the third set would represent the third image. So now you have an even longer sequence that you can just throw through a transformer. So I don't know, I think this is kind of the current state of like video modeling, which is very naive. There isn't much going on. All you're doing is you're flattening your sequence. You're just treating this like an image task. So it's very, very naive. There needs to be more added to it. And that's probably why you see the images, or you see videos created now where they're not temporally consistent. They're not that good. It's just because you're flattening them and you're treating it like an image, but it's not an image. It's a sequence of images. To add on top of that, the loss is exactly the same. So the loss is equal to the velocity prediction. So the velocity is equal to epsilon minus x0. And basically, you just have your model predict the velocity. So this would be the velocity prediction given the noisy image. This is just your mean squared error minus the actual velocity squared. So mean squared error of the velocity prediction and the actual velocity. Yeah, and all you do is you just change the dimension of this, and that's it. So initially, this seems like a fine idea, but the problem is like the model isn't going to learn these temporal relationships, and that's what they show in the paper here. They basically say, what if we shuffle the frames? So assuming, let's just train the model in this naive way, and let's shuffle the frames. Let's permute it in some way. So they say they conduct an experiment with two variants of videos that are fed into the model. First, the plain video without shuffling, and second, the video after applying a random permutation. And they basically find that if you permute the frames, the model, like, it gives almost the same prediction. They say the result of this experiment are reported in figure 3. As can be observed, the original model appears to be nearly invariant to the frame shuffling until step 60 of generation. So, like, and if you look at the mean squared error loss, that's intuitive. It doesn't have anything to model the temporal relationships. You're just hoping the model will learn that via reconstructing this image or reconstructing this video. So there's nothing forcing the model to learn these temporal relationships. So what they do is they say, well, what if we condition the model on these temporal relationships instead of just having the model predict the mean squared error or just predict the velocity, just like a normal image, what if you actually add motion to the model? So there's this model called Raft. I may cover it. It's an interesting model because it gives you the motion for 2 frames, or it gives you the motion of a video. So if I have, say, 2 frames and there's something moving here, some stick figure moving, it'll basically give you the motion of every pixel. So the output will be, so like your input video is going to be of shape T by H by W by C. And your output will be, I guess it would be T minus 1, but I'll just write T. T by H by W by 2, where this represents the velocity of every pixel. So kind of the direction, or the direction that the pixel's moving in. So like if I have these pixels here, they would all point in this direction because the stick figure is moving that way from this frame to this frame. So this is what you get as the output, basically just these direction predictions of of every pixel in the image for where that pixel is moving in this video. And they use a model called Raft, and Raft, you give it this video and it gives you these motion predictions. Not going to get into Raft. I do kind of want to make a video on Raft because it's used for all modern video, or for all modern motion. If you need motion, you use Raft. So I do think it's interesting, and I do think it's a pretty cool model. So once you have these, they basically want to concatenate. They basically want the model to predict both the image part and the motion part. So given an image here, you want the model to reconstruct, or given a video, you want the model to reconstruct that video using the normal mean squared error loss up here. But you also want the model to reconstruct the motion, and that is to inherently build this motion into the model. So the way they do that is by concatenating the two representations. So you have your image here and you have your motion. You concatenate these two and you're going to feed it through the model, and the model is going to have two objectives. One objective is the reconstruction of the image, which is the normal velocity prediction here. And the second objective is going to be the exact same objective, except replace xt, so our image or our video, with the motion. Now the problem here is we have a latent diffusion model, so we have to put this in pixel space. Right now it's in motion space. It has these velocities, so all you would see here is a bunch of velocities. That's what you're given, or not velocities, but a bunch of directions, a bunch of vectors representing how these pixels move. A cool thing about this representation is you can convert it to pixel space. So the way you can do that is by saying, if I have, it's over here. So I have these directions here, U and V, saying where pixels are moving to in the image. So here, it's 2 dimensions because it's a vector pointing in a 2-dimensional space, saying where is this pixel moving. So yeah, given this representation here, you can take the magnitude of this direction, and you can take the angle here, and you can convert that to an RGB code, to an RGB value. So given a pixel here, you have a motion direction, and you have a motion angle here. And you can take that and you can map it to an RGB value where the magnitude is basically the intensity of that pixel, and the angle is the RGB value, and you can get that from the color wheel. So you can map this to RGB space. So you can map motions to RGB space, and it's the same representation. It's storing the same information. So that's what you see here. They map it to an RGB space from the motion space. So now that we have this in RGB space, so we converted these motions to RGB values, technically we have an image or a set sequence of images. So the motion for every frame in our image is now an RGB representation of that motion. Theoretically, we can feed that into our variational autoencoder, and it will output and it'll encode this information. So I'm a little skeptical about this. So basically, you have your input data here for our variational autoencoder, and a normal variational autoencoder will take this and it will downsample the image. So if we just have one image, it'll downsample this, so our encoder, it's a 3, to a smaller representation. So if this was height by width, maybe this is h/8 and this is w/8, and our decoder will take this and it'll map it back to h by w. And then you have your channels as well, but I'm not going to worry about that. And you do your diffusion process in here. So if you have a temporal autoencoder, you basically add some frames and you also downsample time, THW. So you can downsample time by maybe a factor of 8, whatever you want that to be. So this will now be a compact, or it'll be a compressed representation along both the spatial and temporal axes, and your autoencoder will reconstruct that H and W here. So this makes sense for an image. Like, you basically train this on just RGB images or RGB videos, and you get a good VAE for videos. So this representation here will, or this part here will model time and space in some way. Inputting this here, this is a, like, technically it's an RGB image that we're feeding into the variational autoencoder, but it's not representing the same thing that an image is representing. Like, an image is representing an image. It's just a normal image you would find out on the internet. That's the input distribution that the model is expecting. But this is not a, like, technically it is an image you would find out on the internet, but it's a different type of image. It is sure, it's an RGB image, but it's not representing the same thing that an RGB image is representing. So I don't know if this space here. Like this space is really good at representing RGB images in the natural world. It's not very good at representing, like I feel like there's probably a better way to compress this information using the variational autoencoder. Because basically what they do is now that you have your pixel representation of your motion, they just feed it into the autoencoder just like a normal image. But that feels wrong because the autoencoder is trained on natural images, not on it's trained on natural images, not trained on motion. So I'll talk about that. I'll talk about something later. Like I think this can be changed in some way to be a little bit better. Like it's a first idea that works well, but I feel like it can be made better in maybe future work. So now that we have two representations, we have our image representation in image space, so that's easy. And we have our motion representation also in image space because we mapped it using the magnitudes and the angles to RGB values. We can throw both of these through our variational autoencoder to get a latent representation. And using this latent representation, we can then do our normal diffusion modeling. So that is, yeah, and that's why they have to map it to pixel space. So now that you have these two representations in latent space, you can then you do your diffusion modeling. So what they do is they first train a diffusion model on videos just by themselves. So just a normal video diffusion model that was mentioned above using the naive, just feed an image in, get the velocity prediction of get the velocity prediction of the noise. So that's what they do for a large part of training. And at the very end of training, they append this part here. So you have this pre-trained diffusion model here that just predicts the velocity of your pixel representation of your image. So you have this pre-trained part. You then take your weight matrices, your input and output weight matrices, and you take your latent representation of your motion. And remember, we get that by throwing the pixel representation of our motion through the variational autoencoder. So that's what this represents here. You append some zeros to your weight matrix, and you just append these two together. So instead of your input being T by H by W by C, it is now T by H by W by 2C, where this represents the three channels from your pixel or from your image and 3 channels from your motion, or however many channels that is. And you just zero append these matrices so that the model can learn how to predict this. So let's go over to the loss down here. So like I said, the loss is exactly the same. All you're doing is, instead of just predicting the image, you also predict the motion. So we append the motion and we append the image representations together. You feed that through your diffusion model, and then you get your output predictions for your images and for your motion. So the loss here is modeling both of those. So you have your velocity prediction for your image and you have your velocity prediction for your motion. So you're just treating the motion the exact same way you treat, I keep on saying image, your video. You treat the motion the exact same way you would treat your video. So the input will be T by H by W by 2C, and the output will be T by H by W by 2C. So it's the exact same loss. You're just appending on this motion part. And this is really just a condition. Like it's really just a condition you're adding, just like text. So text, you just add it, and you don't really, like, I mean, in this case, there is no output for the text, but there is output that the model has to predict for the motion, but you don't need that whenever you're doing inference. So for inference, you use this as a condition rather than using this as a useful prediction. So you're really just guiding this model with the motion, and it's a very, very hard guidance. So now we have two different guidances. We have text guidance, which is guidance using cross attention or something similar to that, maybe a dual stream if you're doing a stable diffusion 3 architecture. So you have these two conditions, and you have your motion condition, because we don't care about the output. This is really just to help the model out with generating a temporally consistent video. And you have your text condition. And they derive this equation, basically a new CFG equation, stating that, I mean, it's very similar to the old CFG. It's just adding this motion prediction. So normal CFG is just, you have your image part. So it's 1 plus W, or I'll call it alpha. Alpha times your model. So your model given xt and your condition y. So this is just your text, plus alpha times your velocity prediction of xt given a null class, or minus. And basically what this is saying, where alpha is in 0 to infinity. I think it's actually, I don't think you can actually include 0. But anyways, basically what this is doing is it's saying, here is our class conditioned part, and this is our class unconditioned part, and we're basically going to remove the null class. So whatever the model would have predicted versus without the class versus what the model predicted with the class, and you're basically removing null information to emphasize this class here. And you do the exact same with your motion prediction. So here, you have your prediction using both motion and text. So this is just the first term here. But we have 2 weights here. So we have 1 weight for the text and 1 weight for the motion part. This is removing the null prompt information, and this is removing the null motion information. So it's the exact same idea, except you're doing it for both text, or whatever condition that may be, and the motion. So we're using this as a condition. We're not using it as an actual useful prediction, although we're modeling it as a useful prediction. So this kind of gives 2 different ways you can model a condition. You can either model a condition using kind of a light condition, saying like text is a very light condition. It's there. The model can use it if it needs to, and it ends up using it because it finds it useful. It finds it useful to minimize the loss. But it theoretically doesn't have to use the text. There's nothing forcing the model to use the text at all. It's there if it needs it. This is a very hard condition. We're saying the model must learn how to use the motion because it must predict the motion. So there's kind of these 2 ways you can condition the model. Either a hard condition, using a loss making the model predict the motion, or a soft condition where the model wouldn't have to predict the motion. Maybe you can do that via some cross-attention. And I am very curious to see, does the model need this hard condition here? Or if you just treat it like text and you just condition the model on motion, just like you would with text, does it do as well? Because this is this is a lot of it, or it's not that much. You basically just append 3 channels, but I'm curious if you actually need the model to learn this loss, or if you can just have a light condition and the model will do just as well. So that's something that they don't do an ablation on, but it's something I'm very curious. Can you just add a light condition and will the model be as good? But yeah, it's basically the paper, and they show that it does a lot better. Things are a lot more temporally consistent, as you would expect, because the model has to learn these temporally consistent representations. And they mention that in the first part, remember how we permuted the frames and the model basically did the same, like the model would output pretty much the same prediction. That's bad because if you permute the frames, the prediction should be completely different, assuming it understands motion. And they say, once they add this motion part, once they add the motion prediction, it is completely different. So that's a good thing. That means the model is actually using the motion part. They mentioned down here in some ablations that without optical flow, the model does significantly worse. And they also mention some other things, but the main part is without optical flow, without the flow part, it does significantly worse. So yeah, pretty short, easy paper, but I want to mention a few things. I think this is a very important thing that you should add to a model. You should be adding motion information. However, I think the way they do it is kind of a little, it's an initial method. And it works quite well, but I think it can be made a lot better because it is just a first implementation. The first implementation is never the best. And I think one way that you can make it better is, well, first see, do you need a hard condition or can it be a soft condition? Can you just guide this using a text-like procedure where you just have it there and the model can use it if it needs it? Or do you need a hard condition for the model to actually utilize this motion information? That would be something interesting to experiment with. So like you could just add this as a cross attention or something. Does it do as well if you do that? Another thing I would be interested in is, can you change the variational autoencoder? So right now we have the variational autoencoder, which just takes in the 3 channels as its input. I'll just call this C and I'll call this 3. So it takes 3-channel RGB input and it outputs a 3-channel RGB output. And this here is a compressed representation of time and space. What I'm curious is, can you append the 2 frames or the 2 channels representing the motion from Raft? Can you append these two to the original image and encode this into the variational autoencoder? So this space here would now represent both. It would be a joint space. It would represent the image space and the motion space. So instead of just lightly just compressing time, it has to be a joint. It has to be a joint image and motion representation space, and then have it reconstruct the motion as well. So that means both the encoder and decoder have to learn how to deal with this motion information. So that means this latent space would not just represent the video, but it would also represent the motion as well. And then you can have your diffusion model do like you would have some number of channels, and it would work with that. It would work with that in a better way than just than mapping this to an image space. I feel like mapping it to image space and throwing it through or pixel space and throwing it through a normal variational autoencoder isn't the best way to do that. So I'm curious, can you make would a variational autoencoder that has motion information be better than a variational autoencoder that does not? How would the videos be better? Another thing is, like, is a Gaussian prior the best? I mean, it probably is. If you just throw Gaussian, it always works well and it has nice properties. But I wonder if it would be better to go from no motion, so using kind of no prior, or like a 0 prior, to an actual basically modeling no motion to the motion prediction. Like, that would probably be annoying to model because it's not Gaussian, so you don't get these nice formulas, but just some other side note. So yeah, mainly I think this is a very important, it's very important to add this this motion information. And I think it's a really good direction that video models, to add actually temporally consistent video models, which we do not have right now. Most video models are not temporally consistent. So yeah, cool paper. Just wanted to talk about it and give some thoughts about it.